Gun violence remains an alarming public health issue in America that disproportionately impacts low-income urban neighborhoods. In cities such as Chicago, youth from gang-affiliated communities must navigate the risk of violence in their daily lives. Social work research shows that gang-involved youth increasingly turn to social media when they experience violence and the loss of loved ones. Furthermore, their loss may escalate into aggression towards rival gangs and ultimately into plans for retribution. Thus, identifying aggression and loss on social media can actually help detect potential violence in its early stages. Violence prevention organizations are already scouring social media looking for these signals, but it's impossible to manually find every relevant post online. So in my project, we developed a system that can automatically detect aggression and loss in social media posts by gang-involved youth. Our pipeline for automating this task includes collecting and labeling data, designing meaningful features to represent the data, and building a machine learning model to take in the features and predict whether a given tweet expresses aggression, loss, or some other emotion. First, we begin with data. We sought out the help of domain experts from Chicago so that we could ensure the highest ethical standards in identifying users and interpreting their posts. Our experts included youth from gang-affiliated communities and local organizations who are familiar with mediating gang violence. They helped us identify 279 representative users, and we scraped their posts to build an unlabeled dataset of over 1 million tweets. We then took a subset of the tweets and worked with our domain experts to label them as aggression, loss, or other. The next step was to design meaningful features to represent the data. First, we wanted word embeddings, which are real valued vectors that represent the meanings of words and capture analogies between them. We also wanted to have a lexicon that mapped words in our vocabulary to key emotions, such as aggression and loss. However, our challenge here was that our users spoke a specific variant of African American vernacular English that was not captured by any existing embeddings or lexicons. So we had to construct our own resources. First, we used the tool Word2Vec to train word embeddings on our dataset. Next, we adapted a graphical algorithm to automatically induce an emotion lexicon. As input, the algorithm takes in a seed set of words that are most indicative of some emotion. The algorithm then propagates the labels from the seed set over a word graph by iteratively running random walks. Using this method, we derived aggression and loss scores for each word in our vocabulary. Another challenge was how to represent context, since context is critical for interpreting emotion. To address historical context, we built features that captured the user's recent posts leading up to the tweet in question. Given a set of history tweets, we first translated each tweet into its word-level representations, which were either word embeddings or lexicon scores. Then we aggregated the word level to create tweet-level representations, then aggregated the tweet level to create context level. When we used word embeddings as our base, our history feature captured what the user had recently said, but when we used lexicon scores, our history feature captured what the user had felt. In our experiments, we found that these types of history provided different, yet both valuable sources of information. To address social context, we also built representations of the pairwise interactions between users. We defined that two users interacted on a tweet if they were both involved in it, as the author, as a retweet, or as a mention. Then we represented each pair of users by aggregating all of their tweets of interaction and averaging word embeddings over those tweets. Finally, we experimented with a number of machine learning models and found that CNNs were the most successful. We designed the CNN's architecture to take in the text, translate the words into word embeddings, run the embeddings through convolutional layers, apply max pooling, append the context features, and then make its final prediction. In our experiments, we found that even before adding context, our domain-specific resources enabled our model to significantly outperform prior work on this task. Once we added context, we achieved another significant improvement. This showed that we are not only able to improve over the prior state of the art, but also that each of our technical developments made an important contribution to the model. My personal contributions involved spearheading our domain-specific and context approaches. I trained our word embeddings, constructed our aggression loss lexicon, and built the pairwise representations. I also collaborated on designing the user history features, running experiments, and organizing our code to make it public. I was named first author of our conference paper and led the team in our writing process. When our paper was selected for publication and oral presentation, I presented our work at EMNLP in Brussels. Before I move into conclusions, I want to emphasize the importance of ethics in our work. We prioritize the privacy of our users and partnered with domain experts to ensure that we fairly interpreted the data. We make our dataset available to other researchers on the condition that they sign an MOU and agree to our ethical guidelines. The importance of these guidelines cannot be overstated for this work or any other computer science application that involves human lives at stake. In conclusion, this project puts forth new strides in computer science and social impact. Our techniques address the challenges of domain specificity and context, which are applicable to any automatic system that aims to detect socially driven phenomena. These aims include detecting sentiment, argumentation, hate speech, and more, and our work offers the potential to advance the field in any one of these tasks. Furthermore, the strong performance of our model demonstrates that automated systems can effectively detect gang-involved escalation. Our work serves as a pioneer towards ultimately building a system that can help organizations save critical time, scale their reach, and prevent the tragic loss of young lives.